All right, it's the beginning of the semester for Chemistry 315, and I traditionally give an overview of the math needed in 315 because, like all physical chemistry classes, 315 is a math-intensive class, and so let's make sure we're all on the same page. I'm going to cover a variety of topics here, sort of central topics for this particular class. First of all, units, the most basic sort of issue that probably everybody's been dealing with since freshman chemistry, if not before. But in P-Chem it's particularly tricky, and so I will say a little bit about it. We'll see a lot more during the course of the semester. I'll talk about the properties, the mathematical properties of logs and exponentials. I'll talk about 1D calculus, and I'll talk about 2 and 3D calculus, and then finally just a little bit about summation notation. Let me say that I'm not going to be able to say nearly enough to cover these topics at all adequately. The purpose is just to give people a little reminder, especially people who may not have had a math class for a while, people who haven't been in a straight linear progression through their undergrad time. All right, so first of all, on units. As I have said earlier, in P-Chem, units can be very complicated, and we'll see examples of that in the course of the semester. And that means that it's easy to make units mistakes. I make units mistakes. Every Albert Einstein made units mistakes, so shouldn't be considered trivial. We tend to treat them that way in freshman chemistry, or try to anyway, but they really aren't. And so let's just do a simple example with the ideal gas law, PV equals nRT. Pressure can come in bar units, Pascal units, atmosphere units, and there are, of course, other units. Volume can come in liters or milliliters or cubic meters. N, the mole number, is always just moles, so that's easy. And T, the temperature, is always just degrees Kelvin. Don't use degrees Celsius or degrees Fahrenheit in the ideal gas law, of course. I think everybody knows that already. And it's always safe to use degrees Kelvin in every formula that involves temperature. It's sometimes safe, occasionally safe, to use degrees Celsius, but it's always safe to use degrees Kelvin. That's the preferred thing if you have any doubt at all about what to do. And then the gas constant itself, R, can have, well, the most common versions of it come in two varieties. One in joules per degree Kelvin per mole, 8.314, and the other one, 0.08206 liter atmospheres per K degree mole. The difference is the units of energy, and usually we will use 8.314, but from time to time it's convenient to use 0.08206 if the units for the problem match the units on that version of R. So, for example, what is the pressure for a volume of 2 liters, a mole number, just 1 mole, and a temperature of 300 Kelvin? Plugging the units in, let me get a pencil here. You can see that the units work out. There's moles, there's joules per degree Kelvin per mole, and there's degrees Kelvin. Notice that the volume here has been converted to meters cubed for this calculation, because if I'm going to use this value, this MKS unit for the gas constant, then I've got to use the MKS unit for the volume as well. And so doing that, everything in the formula is in MKS units. Again, like I said for degrees Kelvin, if you ever have any doubt about what units are compatible with what other units, always convert everything to MKS units first and then plug those numbers in. It's always safe if you've got everything all in the same system of units, and MKS is the sort of standard default one for this class. There are, of course, other consistent systems of units that you can use, but MKS is by far the most common. All right, with those numbers, you get 1.25 times 10 to the 6 joules per meter cubed. If you just cancel all these units up here, moles cancel, K cancels, you're going to get joules per meter cubed, and that turns out to be the same thing as a Pascal. Pascals are not the most convenient unit to use, of course, so now probably you want to convert that to something more that gives you a better feeling for how many atmospheres or how high that pressure is. So we've got conversion factors for atmospheres into pascals and bars into pascals. And using those, you get 12.3 atmospheres or 12.5 bars. Bars and atmospheres are almost the same. They're only about 1% difference. On the other hand, so that's doing it with MKS units. Because we were given the volume in liter units, it might make sense to use the liter atmosphere version of R. And if you do that, the calculation gives you atmospheres right away. That's a little simpler if it's atmospheres you want out and not pascals. And so in this case, it was convenient and efficient to use the other value of R. But you have to be a little wary to make sure the units are consistent. The liter atmosphere unit is a unit of energy, but it's a very non-standard one. It doesn't belong to any system of units that I'm aware of, any general system of units that I'm aware of. And so using it, you have to be a little careful. I say here that units mistakes are usually easy to catch, and that's because they're usually huge. You get factors of 1,000 or 10 or 100 or 12 or something, giant numbers that you're off by. And so if you have some feeling at all for what kind of answer you should get, and you always should have that, you should always be asking yourself, what's the order of magnitude for the number I should get here? You might not know the exact number, but you should have some feel for how big that number ought to be. And if you have that, then it's going to be obvious usually when you make a units mistake, because you'll be off by way more than you could possibly imagine truly being off. Okay, that's units. All I want to say about units. Logs and exponentials are the next topic. Logs and exponentials are absolutely ubiquitous in Chem. We're going to use them on the first day. We're going to use them every day after probably. And so make sure you're familiar with those. So the log function and the exponential function are inverses of each other, of course. So for example, here's the Boltzmann relationship between the entropy and the number of microstates available to the system, and it's a log relationship, but that means that you can divide through by kb here, and then take the exponential of both sides, right? Take e to the x on this side, e to the x on that side, and since e to the x and log are inverses of each other, that just gives you w, and you get e to the s over kb on the other side, so it allows you to solve for the number of microstates available to the system. If you multiply a log by a constant, then that's the same thing, going both ways, in fact, as the log of something to a power. So, of course, if you've got something to a power, then you can pull it out in front. If you've got something in front, you can put it up as a power if that's useful to you. And likewise, for an exponential, 2 raised to a power, that's the same as e times ax, or the power times the argument of the exponential, and vice versa, of course. You can always go back and put that power up, that a up as a power if you need to. So here's some examples again. S equals kb log w, same relationship. That's equal to log of w to the kb power. Likewise, if you have w, which is e to the s over kb, sorry, that should be a 1 over there, then that's the same thing as e to the s to the 1 over kb power. You can avoid making mistakes sometimes by noting that if you have the logarithm of something, or the exponential of something, or the sine or the cosine, any complicated function of some argument, then that argument has to be unitless. It can't have units like liters or distance or anything like that, meters or something. Has to be a unitless quantity that appears either in a log or in an exponential. And so, for example, in this case, e to the s over kb, which is w, this quantity has to be unitless. And in fact, this constant, the Boltzmann constant kb, has the same units as entropy does. That's by construction, by definition, really. And so that means that this ratio is a unitless ratio, and that makes it proper to put up into an exponential. If this quantity weren't unitless, you would know right away that there was something wrong with your algebra someplace or something, because you can't have a united quantity up in an exponential. Likewise, in the other half of the Boltzmann expression, the quantity w must be all by itself a unitless quantity, and in fact it's just a number. It's like 5 or 10 to the 22 or something like that. It's a unitless number. And so that's also fine, but again, if you've got put something in there with units or got something in there with units from a chain of algebra, let's say, then you made a mistake someplace. If you add two logs, then that's the same thing as the log of the product of those two things. If you multiply two exponentials together, that's the same thing as the exponential of the sum of those two things. You can see why, right? If I take the log of this, I'm taking the log of that thing, which is the product of two things, and I'm going to get just x plus y over here. So these properties have to follow from the fact that the log and the exponential are inverses of each other. And of course, these are the most sort of basic properties of logs and exponentials. I put them here kind of more towards the end, but these are the things that sort of define what a log or an exponential is. And so here's an example. Delta S, the change in entropy between two things, is S2, the final entropy, minus the initial entropy. If I use the Boltzmann relationship again, that's KB log of the final number of microstates minus KB log of the initial number of microstates, W1. That's equal to factoring out the KB log of W2 minus log of W1, and using the property of logs and the power, right? This is really plus W to the minus 1 power here, right? Using the properties of logs. You get then that this delta S is just equal to the log of the ratio of the number of microstates available to the system. This has a lot of implications, physical implications. That's not the purpose of this little lecture, but it does have lots of physical implications later, and we'll talk about that in the course. But what it's saying is that when the entropy changes, it's because the number of microstates in the final state either increased or decreased by some factor over the number of microstates that was available to begin with. So you can interpret what an entropy change means. It means some change in the freedom that's available to the system. And here's just the same thing. I won't go over this because I'm feeling like we're running a little long here, but it's basically just also exercising these properties of logs and exponentials. All right, calculus, 1D calculus. We'll take derivatives and we'll do integrals, one-dimensional integrals and one-dimensional derivatives in this class a fair amount. And one of the most basic properties of derivatives, I'm going to assume that everybody knows how to take a derivative generally. You get lots of practice in that in calculus. Probably people don't forget that even if you haven't had it for a while. One of the basic properties is that if you add two functions together and then take their derivative, you can just take the derivative term by term. It's the sum of the derivatives of the two functions. If you multiply two functions together and then take the derivative, you take the derivative of the first one first, multiply it by the unchanged second function, then add the first function times the derivative of the second function. The chain rule is maybe the rule that's most abstract, but also most widely used in calculus. That says that if you've got some function, and you're taking that on another function, so you've nested the functions, then when you take the derivative, you take the derivative of the first function, leaving the second function in there, and then you take the derivative of the second function and multiply it on the outside. So here it is in words. Take the derivative of the outside function, that's f here, then multiply by the derivative of the inside function, that's g. So there's the derivative of the inside function. Here's an example. This is sort of my favorite standard example of the chain rule. Take the derivative of e to the minus x squared. Well, here's our outside function, right? It's e to the x, or e to the something. And here's our inside function, minus x squared. And so I take the derivative of the inside function first, and that doesn't do anything because the derivative of the exponential is just an exponential. And then I take the derivative, I multiply by the derivative of the inside function, and the derivative of minus x squared is just minus 2x, so that's what goes there. Here are a bunch of common derivatives. I think people don't really need to know this in any way. It's all over everywhere if you want to look them up. Take the derivative of a power, and you get just the power down times the power reduced by 1. An exponential e to the ax is just a times e to the ax. That's an example of the chain rule, of course, with ax being the inside function. Derivative of log is 1 over x. We'll use that a lot, both ways, actually. The integral of 1 over x is log of x, of course. And derivative of sine is a cosine. Derivative of cosine is a sine. We won't use sines and cosines very much in this class because that's just doesn't come up that much. But we will use a few of them, I think, if I remember right. All right, integrals. Here, I've just made a table of all the integrals, I think, that I remember anyway, that we're going to use in this class. Here they all are, 5 of them. If you want to just memorize them, you can. The integral of a power is 1 over power plus 1, x to the power plus 1. Integral of 1 over x is log x, as I pointed out last time. Integral of e to the ax is 1 over a e to the ax. Sine gives you a minus cosine. Cosine gives you a sine. All right, all of that I hope is pretty boring for everybody, but now we get to the stuff that maybe is a little less familiar. That's 2 and 3D calculus. We're going to use a lot of multi-parameter or multivariable functions in this class. All of thermodynamics is full of those. And so we will have to be familiar with some of the basic stuff from 2 and 3-dimensional calculus. The basic difference is that if you've got two variables, or maybe 3 variables, or however many you like, 20 variables is possible, then you don't take just derivatives anymore, you take partial derivatives, right? And what that means, here's how it's written. The derivative of our function x, let's suppose it's this one here, f of x and y, with respect to x, holding the other variable constant, holding the y here constant, means just take the derivative in the ordinary way, but pretend that y is a constant. And that's it. It's easy. If you can take one-dimensional derivatives, you can take partial derivatives. And if there's more than 2 variables, if you've got 2 extra variables in addition to the one you're taking the derivative with respect to, so df dx here, then you just hold both of them constant. You always just hold all of them constant except the one that you're taking the derivative with respect to. So that's easy enough. Let's do some examples. The ideal gas law, again, we're calculating pressure. There are 3 variables, N, T, and V, so we can think of the pressure as formally as a function of N and T and V, 3 variables. So that means there'll be 3 partial derivatives, one with respect to each variable. Derivative with respect to N, holding T and V constant, just means treat all of, treat all of this stuff as if it were a constant, right? And so you're just taking the derivative of n times a constant, which is just the constant, RT over V. This one, take the derivative with respect to temperature, holding n and V constant. Looking up here, that means that all of this stuff is just a constant. And so you're just taking the derivative of T times a constant, so that's nR over V. And lastly, taking the derivative with respect to V, holding n and t constant, that means treating all of these guys as a constant. So it's really just a 1 over V that you're taking the derivative with respect to, and that gives you minus whatever the constant is up on top here over V squared, over x squared, if it were a 1 over x. All right, we will use, right almost from the beginning of the class, a number of expressions that are total differentials. The first law of thermodynamics is usually expressed as a total differential, so we need to be at least kind of prepared for that. The total differential of any function here I've written for 3 variables is the partial derivative with respect to each of the 3 variables in turn times the corresponding little dx, dy, or dz, or differential for each of the variables, and then all added together. And so, again, to do an example with the pressure, PV equals nRT, P equals nRT over V, the 3 partials we just calculated are these 3 guys, and so using our formula up here, this should be the total differential for the pressure when either N or T or V changes. Let me say something about what this formula means in both cases, but especially here in the pressure case. What it means is that if I want to know how much the pressure will change when I change the mole numbers, and at the same time I change the temperature, and at the same time I change the volume. So I'm changing everything at once. But I don't change any of them very much. I just change them a little bit. Then that's what this formula gives you. It gives you the total differential due to all the changes that are happening all at once. And so it's very convenient. It's, as long as the changes are small, it's really easy to calculate all the changes that took place, even when a whole bunch of complicated things are happening at once. All right. Here's an example of the first law of using a differential. The first law says, and this is from experiment now, it says that the total change in the internal energy of any system, any thermodynamic system, is the temperature times ds, is the pressure times dV, or minus the pressure times dV, and then something called the chemical potential, probably less familiar to people, times the change in mole numbers, dN. And first of all, right off the bat, you can say, just from looking at this, what the basic variables that the internal energy must depend on are, right? Because if the differentials here are ds and dv and dn, then u must be a function of s and v and n. These little differentials are labeling the variables that our function depends on. Second, we have this from calculus, right? This is from experiment, and this is from calculus. They're two different things. This thing doesn't come from that thing, or vice versa. These are two separate statements. And that means that we can identify this, right? That must be the same thing as that. This must be the same thing with the minus sign as that. And that must be the same thing as that. And so we can identify, there's many, many thermodynamic relationships. Here's some of the most basic and important. It allows us to identify and even kind of define what the temperature is. Thermodynamically, it's the derivative of the internal energy with respect to entropy holding volume and mole numbers constant. Notice that all these things, if this had something else being held constant, if this were temperature and mole numbers, that wouldn't work. The things held constant count and matter. This thing is only true if all the stuff in here is correct. So likewise, minus the pressure is the same thing as the change in the energy with respect to volume holding entropy and mole numbers constant. And the chemical potential is the change in energy with respect to mole numbers holding entropy and volume constant. All right, that is all I want to say about 2- and 3-dimensional calculus. We'll do a lot more, and as we're going through, I'll try to introduce things slowly enough so that people can keep up even if it's been a while. Finally, the last little bit, I want to talk about summation notation. We won't use this much, and the place where we're going to use it is mostly right here in the example that I give. There's something in statistical mechanics called the partition function. It's probably the most basic quantity in statistical mechanics. It allows you to calculate all these other quantities that we've been talking about up above, all kinds of thermodynamic properties. And what it is, it's a great big sum. So the system has certain energies, E0, E1, E1000, and everything in between. And you take exponentials, divide each of the energies by kT, put it up in an exponential, and then you sum those exponentials in one giant sum. So this particular case has 1,000 terms in the sum. I can always write it out like this, right? There's nothing wrong with writing it out like that, but it's kind of clumsy, takes up some space. So there's this stuff called, this thing called summation notation. You can write the same sum as a big capital Greek sigma with an index, I, that runs from 0 up to however far, 1,000 in this case. And then you put the index here to indicate that you're summing or running over all the possible values of I. And that means the same thing as all that up there. So yeah, like I say here, just a more compact way to write a great big sum. All right, that's it. I hope people have questions, you'll ask at the next help session or recitation section. Thanks.